Okay, I'm going to go ahead and get started. I have a lot of issues to cover today. I want to talk about the presentation of statistical results in published studies and just some of the issues that have been that I've found in both reading and then writing articles for publication. So in terms of my outline here, I want to spend some time talking about classical statistics because I think sometimes that investigators don't really understand what they're doing when they do statistics, but that's just kind of my opinion. And then I want to talk about presenting general linear models. All these are regression models and generalized linear models, time to event models, and then end up with just a summary of presenting methods and results. So a few years ago, there was a big to-do about the use of p-values in the scientific literature. And the argument probably still is somewhat going on today, but they relate back to the use of p-values and the ideas and concepts related to that that are due primarily to Fisher and Neyman. And their writings are almost 100 years old now. But anyway, there's there are people who've always been critical of the use of p-values. More recently, some have advocated for abandoning the concept of statistical significance. So I want to take a look at this and going back to Fisher and Neyman. Fisher viewed the p-value as a continuum, and then if it was small enough, then he would take that as indication that he could replicate the experiment again. And when asked by an associate what would be a small enough p-value, he just kind of mentioned 5% as a offhand remark. But as I'm sure we all know, that's kind of become a standard today, even though that's not what it was meant to be. And for Neyman, his idea was that you set the alpha error before you do the experiment, and then do a power and sample size calculation, and then your decision is either reject or fail to reject the null hypothesis that there is no difference. He never indicated that 0.05 was sort of like a magic number, or any number for that matter. So a few years ago, the American Statistical Association came out with this policy that we should stop using the term statistically significant or significantly different, p less than 0.05, or non-significant. And this is found in the American Statistician from 2019. I have that as a reference at the end here. You can take a look at that if you like. So what I take away from this is the concept of how p-values are misused in the medical research literature. And there's two issues here. And one is that the idea of statistical significance has become almost the sole criteria for concluding that you have meaningful or important results. And what I want to show, that's just one element of finding meaningful or important results. And then the other one that I want to talk about is multiplicity, that is doing multiple hypothesis testing where you have p-values for a large number of variables. So just to review from the classical concept of statistical hypothesis testing is that you take a research sample, or you get a sample from a population of interest, and this sample can be random, maybe not, but that's basically what we're doing when we do scientific research. And so the question is a sample representative of the population? And so in the classical view, the statistical significance is based on the concept if you were able to get an infinite number of random samples from the population, they would each be an estimate of the population parameter. Let's say it's a mean. And if you drew an infinite number of these samples from the population, then the mean of the samples would equal the population mean. But of course, we can't get an infinite or even probably two samples from the population. Your research is based on one sample that you draw from the population of interest. But this is the basic idea of random sampling over and over again. What would you discover, or what would you conclude? So when a statistical decision is made, and this is the Neyman's view, is that it's bivariate. It either is significant or isn't. And that decision is based on an a priori selected alpha error rate, the p-value. And so obviously, because it's based on a probability, we could make the wrong decision. And so the two types of errors that we encounter are the alpha error, which is a wrong decision in that we reject the null hypothesis. That is, we say there's a true difference in the population when in fact the null hypothesis is true, that there's no difference in the population. And then analogous to that, the beta error is also the probability of making a wrong decision, but that's the decision where we fail to reject the null hypothesis. That is, we say there's no difference in the population when in fact the null hypothesis is false. That is, there's a true difference in the population. So one thing that we need to understand is that both alpha and beta are arbitrary. The 0.05 has become an entrenched tradition, and so virtually every article, research article, medical research article you see uses 0.05 as the cutoff for statistical significance or not significance. However, if we set something else like p being less than 0.01, then if you got a p-value of 0.05, that would not be statistically significant. In other words, you would fail to reject the null hypothesis. But what that means, and the same thing with p less than 0.05, is that for over an infinite number of random samples on average, you would make a wrong decision one time out of every 100 random samples. So p-values then is a preset level, and that's the important point here, is that we set our alpha error rate for rejecting the null hypothesis. What p-values are not is the probability that the null hypothesis is false, or the probability that the alternative hypothesis is true. But probably even more importantly is that the p-value is taken often to be an index, and the only index of importance or meaningfulness. And I'm sure you're all aware of the fact that at least in the past, non-significant p-values have a lesser chance of being published than significant ones. Sometimes you've seen, although this might not be the case, becoming less apparent, but you've probably seen the term highly significant, and that's typically given when the p-value is, say, less than 1 in 1,000 or 0.001. But that's a value judgment, highly significant, and so that's should not be used in declaring something significant. Once you've set the alpha level, it either is or it isn't. And then another concept that often appears is a trend towards significance. And so if you get a p-value of 0.06, but you've set your alpha error rate at 0.05, then that would be, you'd have to conclude that's not significant, but is that big of a difference? So you can see that the test of significance is not the only or even the most important concept in determining whether our hypothesis is true or not. And so what I want to cover here for several examples is the misuse of p-values in medical research. And so I have here kind of a typical paragraph, statistical methods paragraph you might see in an article. And the important sentence here is a p-value less than 0.05 was considered significant. Here the statement is, even though it means that a 5% alpha error rate means that we'll make a wrong decision 5% of the time out of repeated sampling. But here it's like, it's almost stating that if it's 0.05 or less, then we have a significant or a meaningful or important finding. And so I want to use an example from a published article here a few years ago related to myocardial infarction and cardiac arrest in patients with the experienced shock after the MI or the cardiac arrest. And so this is the abstract from the article, but there's a few things that I want to point out here. We don't need to go into all the details, but basically what they did is they took patients from two different randomized studies, Neuroprotect and Coma Care, and then they randomized those pool of patients to those that had a mean arterial pressure of 65 versus those who had pressure of 80 to 100. And so the primary endpoint that they're interested in here is the area under a troponin curve. And so then they present the results. Just a couple of things here that we're going to look at in their presentation of the results is their area under the curve was lower in patients assigned to the higher MAP target, and their p-value here is a 0.04. But they also make a statement here that is a statement you don't want to make, or that unless you've actually tested that you actually can't make. And so they said that survival with good neurologic outcome at 180 days was not different between both groups. Well, they're not testing whether the differences or whether the survival is the same or not. And so they have an 11% difference here, 64% versus 53%. And the odds ratio of that is 1.5. So what that means is that the one group has a survival rate of which the odds are 1.5 times greater than the other one. So, and then the 11% absolute difference, well, is that just because that's not statistically significant, does that mean that it's not important or not meaningful? Well, maybe 11% is, and odds ratio of 1.5, 1.5 times greater, that's fairly large. But so anyway, that's some of the issues that they have in their study. And so what I want to do is I want to go through some of their specific presentations here. And we'll start out with table 1. And so they have, first of all, the two data sets here, the ComaCare and the Neural Protect. You can see that the ends are fairly small. So as they mentioned before, what they've done in their methods is they've taken patients from these two studies, and they've taken the ones that have an MAP greater than 100 or greater than 80 and ones that are 65. And so here you can see that the table 1, which is a typical table of baseline characteristics, demographics, medical history, and so on. And so they've calculated a p-value for each one of these. So here we have an issue with multiple testing, hypothesis testing, even though looking at the differences in baseline characteristics is not really their hypothesis that they want to test. And so you can see that all these are not significant, which is, if you have a randomized study, that's what should be the case. But the fact is that you've treated each one of these as a test of a hypothesis by using the p-value. And then they have table 1 continues here with arrest characteristics, admission characteristics, and they present a p-value for each one. And then in table 2, they do the same thing with angiographic findings. And so just in tables 1 and 2, we have, I think it's over 18 different tests of hypotheses. And so we come to their table 3, which is the important one here as far as their endpoints are concerned. And so their primary endpoint is the area under the curve, but they have 4 other endpoints that they term secondary endpoints that they also do a test of a hypothesis, whether there's a difference between the two groups. And so here is their finding for their primary endpoint, that they have a p-value of 0.04. So according to their criteria, they're going to say that this is statistically significant. But here for our endpoints, if you want to do a hypothesis test for each one of these, then we have 5 different tests of hypotheses. And so we're doing multiple testing here. And if you do something as simple as a bone-Ferroni correction, which is dividing your alpha error rate by the number of tests you do, so we would have 0.05 divided by 5, which means that of these 5 different tests of hypotheses here, you'd have to get a p-value of 0.01 in order to declare it statistically significant. And of course, that means that none of these would be statistically significant if you made a correction for the type 1 error rate. And then they make a statement here, which shows up again in their, it was in their methods section, but say that p-values for all secondary endpoints are exploratory. Well, that's a nonsense sentence. If they're exploratory, then why are you doing a test of hypothesis? So what I think is typically meant by that is that, well, if it's exploratory, then we don't have to worry about inflating the type 1 error rate. And so multiplicity here is a huge problem in, or it has been anyway, in medical research. And basically what happens if you test a large number of hypotheses, then you inflate the alpha error rate. And so you're increasing the probability of finding statistical significance just by chance. And so if you have, we tested all these hypotheses and they considered 0.05 as the significance level, then you need to make some sort of correction for inflating the type 1 error rate, and often that's not done. So there's a couple easy solutions to this. One is don't list p-values in table 1 or in any table where you're not focusing on your primary outcomes. And in fact, I believe the New England Journal now prohibits listing p-values in table 1 where you're comparing just demographics and clinical variables. The other thing is to use standardized differences. Basically, what that is calculating an effect size regardless of what the sample size is. And so a standardized difference is not testing the hypothesis. It's just presenting what the difference is between, say, two groups or more groups in standardized units. So that's a better comparison for your non outcomes that you're or the outcomes that you're really interested in. And I'll just quickly kind of give you some examples here, or define what a standardized difference is. And basically what it's looking at is the percent of non-overlap in the respective distributions of the sample statistics. So you can kind of picture it as this, whereas panel A, there's not much of a difference. The effect size or the standardized difference is not very large, whereas in panel B, it's quite a bit larger. And so these are the formulas for a difference of two means or a difference of two proportions, and basically a t-test, except that, or it's like a t-test, except that the error term is just dependent on the variance, not so we have the standard deviation of the difference, not the standard error of the difference. So in other words, formulas here don't have an n in it, so we're not computing a standard error. We're not actually doing a test of hypothesis testing. And so if we did that for their table 1 here, this is sort of what we would get. And you can see that all of these differences are pretty small. They're all less than 0.2, except for 2 of them. So that might be important to consider, is that is there some difference related to previous MI and arrhythmia that we might need to have considered. And so this is just a table of the standardized difference and then the percent of non-overlap. And so you can see that as the standardized difference gets larger, the non-overlap between the distributions gets larger and larger. So this is the from your statistical methods paragraph from that article. And they said that all tests were two-sided and assessed at a significance level of 5%. And then here's their, again, use of the exploratory argument, I guess, because of the exploratory nature of the study. No adjustments were made to the significance level to account for multiple testing. So they're aware of multiple testing, but they're just going to kind of wave their hand and say it's just exploratory. So what I've done is written a better, at least in my opinion, statistical methods paragraph where we use standardized difference to compare baseline characteristics and secondary endpoints, unless you actually want to include the secondary endpoints in hypothesis testing. And so I put in here that the alpha error rate for assessment of random sampling error with respect to the difference in AUC was set at 0.05. So that's really what is meant when people say a p-value of 0.05 was set as significance level. That's really what is meant by that you're assessing what the probability is that you're going to get a difference just by random sampling error. And then in the results section, they then say that 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 the difference in one of the groups with shock was associated with a significant reduction of myocardial injury. So here they're using the term significant, and the only thing that could mean is that they're talking about the significant significance from the test of hypotheses. In other words, that P is less than 0.05. But a better way to do that is to, when you present the results, just to say, well, this is the difference. So we could say that after AMI, it was associated with a 37% reduction of myocardial injury. And then in parentheses, you would put P as equal to 0.04. I've just kind of put in the random sampling variability error to make sure we know what we're talking about. But rather than use the term significant, just put in what the actual finding was. So basically, we include here that the p-value is just one check box for study validity. And then if you have comparisons that you need to make, which for a randomized study isn't really particularly necessary, although it's always done, because the randomization should have balanced out the two or more groups that you're doing. However, if you're presenting results from an observational study, then you definitely do need to do a comparison of the demographic and clinical variables. But instead of using p-values, use standardized differences. And then, as I've mentioned before, in reporting results, don't use the term statistically significant or non-significant. Just report what the findings are. In your discussion section, then you can speculate about whether this is significant or not in terms of clinical importance or clinical meaningfulness. But just remember that statistically significant just means that it's a probability that you could have gotten the results just by random sampling variability. I will say that I, at least since the ASA came out with their comment or with their policy on not using statistically significant, I think it's had little or no impact on medical research, because you still see p-values inserted in there with the term significance. Okay, so that's sort of my soapbox presentation of the misuse of p-values. What I'd like to do now is sort of go through different statistical analyses and what is the best way to present those, or what you need to have in the presentation of your results, regardless of whether they're statistically significant or not. So the general linear model is where we have a dependent variable that is continuous, like weight or age or something that can be considered continuous. And then in our regression equation, then the x's represent the independent variables, or what we call the covariates, and then the b's, or the beta if we use the Greek notation, are the estimated regression coefficients. And so the b's, or the betas, are the change in y for every unit increase or decrease if the coefficient is negative in x. And if we have a multivariable model where we have a number of x's, then the beta coefficient is adjusted for all other variables in the model. And the dependent variables can be a mix of continuous, ordinal, or categorical variables. And then the statistical test that we do is whether the regression coefficients are different from 0. So we have a couple special cases of GLM. If we have just one independent and one dependent variable, and the independent variable is dichotomous, then we have that's a t-test. If all of the independent variables, all the x's are categorical, then we have analysis of variance. And if some of the x's are continuous, then we have analysis of covariance. And then if we, on top of that, have repeated measures, so we get a measurement from the participants in the study at time 1 or baseline, time 1, time 2, etc., then we have what's called a mixed effects model, because what we're doing is we're measuring the same variable in subjects or patients over some time period. And so here is an example of the output, a typical output. In this case, we've regressed cholesterol on age. And so just a couple of things in here that you see that in this table that's pretty typical is over here you have what's called the root mean square error. Okay, this is just the square root of the error mean square, which is the what we call the residual in a regression, regardless of what the regression is, whether it's continuous or dichotomous or categorical outcomes. But in regression, you have variability that's due to your model or to the independent variables, and then you have variability that's not part of that, that's left over, and we call that the error variance or the residual variance. And then in our output here, we see that we get for age a regression coefficient of 5.3. That means that for every increase in, or for every 1 unit increase in age, cholesterol goes up by 5.3 units. And then the constant that you have down here, 102, in just a simple regression like this would mean that the intercept, which is the value when the independent variable equals 0. So that's the intercept when age would equal 0. But of course, age equal to 0 isn't very meaningful. So what you typically want to do, or what you should do in this case, is to do what we call center the independent variable. And so if we centered age at 40, then we would take everyone's age and we would subtract 40 from it. So in this case, we get a constant term of 315, which is more meaningful because what this means that this is the value of cholesterol when age equals 40, which is more meaningful than having a value at age equals 0. And so when you see linear regression, and if they give a graph, they present a graph of it, this is what it should look like, where the straight line is the fitted values, that's the regression line, and then you would have a 95% confidence interval, which is not straight because you can see that the 95% confidence interval gets wider near the tails or the extreme values of your independent variable, which of course you would expect because the equation of cholesterol as a function of age would be the best at the mean age, which in this case is around 40. And then, although you don't see this in studies in the presentation of papers is that you need to do regression diagnostics. In other words, to determine whether the regression equation that you came up with is valid or not. And so we do a residual analysis. We can look for outliers, although probably more appropriately, we should name that influential outliers, because some outliers don't really influence the regression equation that much. And then collinearity is the idea that there's a high correlation between your some of your independent variables in the equation. So this is what we call a normal QQ plot, where our residuals are plotted against the normal distribution. And so this is what you should see if our assumption is met that the residuals are normally distributed with a mean of 0, that all of the points in the plot would fall along the line of equality there. If it, in this case, you see, I mean, there's always going to be some deviation, but here we would have a pretty good fit of our regression because the residuals meet the criteria of the 0 mean and normally distributed. And so if we would plot our residuals against one of our or more of our independent variables, then it should look something like this, that they would be randomly distributed around a 0 mean. On the other hand, if you plot residuals against, say, one of your independent variables and you get something like this, then we've got a problem, because we see that the greater the age, that the residuals become very spread out and are not normally distributed across the mean of 0. And so I wanted to show here just an example of a study where we used linear regression in the analysis. And so what we're looking at here is the effect of PCI, percutaneous coronary intervention, on quality of life in coronary disease patients. So the statistical analysis that we did here is pretty involved. I just want to look at some highlights here. So our main analysis was looking at a longitudinal analysis where we looked at quality of life responses over time at baseline, then I think 3, 6, 12, 24 months, and so on. And of course, whenever you have a study where you have data over time, you're going to have missing values. And it turns out, of course, as you would expect, that the further out in time you go, the more missing values you have. And so typically what is done is that you assume that the data were missing at random. In other words, that means missing at random means that the missingness is not related to your outcome. But of course, in longitudinal studies, that's probably not the case, because as you go further out in time, the people who are responding are probably the more healthy people, and others are dropping out because of poor health or death or whatever the reason might be. So it's not missing at random. And so we also needed to look at whether the pattern of change over time was linear or nonlinear. So we accounted for that. And then we did another analysis where we assumed that the data was not missing at random. In terms of a presentation of results, this would be the main picture that you would want to see, because a plot, when you have repeated measures data, a plot of the data over time is really the best way to communicate what the results are. And so you can see here that we have, for the different components of the Seattle Angina questionnaire, essentially the same pattern over time, where scores are lower at baseline, and then after the intervention they increased, and then they level out as time goes on. And I think almost every study I've ever looked at that looks at some measure of quality of life or treatment satisfaction or whatever over time will look like this. And so what we can conclude, and what was concluded, was that initially patients that received PCI rather than just medical therapy alone did better out until about 24 months. So not in every case, but then the two groups were essentially the same. So this is a typical pattern that you see in doing responses to patient questionnaires or patient-generated responses. And so in the conclusion, then, that's the essential conclusion that we came up with. And you can see that we don't use statistical significance here. We just sort of generalized to what the overall findings were, that you had a greater benefit from PCI in patients 3 to 6, 12 months out from treatment, but after time, more time elapses and the treatment effect disappears. So then I want to talk about probably one of the more common analyses that you see, what is known as the generalized linear model. And usually you see the binary logistic regression model, where we have a dichotomous outcome, yes, no, dead, alive. And so in this case, although the equation looks fairly similar, what we're modeling is the log odds of one of the events. And so we have the log of the probability of the event over 1 minus the probability of the event, which is the odds of the event. And so our log odds, then, when we solve for our regression coefficients, if we exponentiate those, then we get the well-known odds ratios. And this is true, technically speaking, is true for a non-randomized study, or it's a retrospective study. If the design is prospective, then it's referred to as the risk ratio. And so basically here, the test is whether the odds ratio is different from 1. Because if the odds ratio is 1, that means that the probabilities are the same in each group. And so in the logistic regression or any other type of regression, whether you have categorical outcomes, then if the 95% confidence interval includes 1, then that means that the odds are statistically the same for the values of the categories of a given covariate. So like in the case for the general linear model, we have a special case of logistic regression where if the treatment is dichotomous, and of course our outcome is, then we have a 2x2 contingency table where we can calculate the odds ratio by taking the ratio of the cross products of cell A times D divided by cell C times cell B per C. So in any case, what we want to do in looking at, as far as interpreting our odds ratio, I have an example here of whether PCI inpatients were readmitted 30 days after discharge. And so our outcome is either readmission, yes or no, at 30 days. And so then the odds ratios for the different variables that we have in our equation, you can see that the odds ratio for age, which is in this case age for every 10 years, is that the odds ratio 1.25 means that the odds of being readmitted goes up by 25% for every 10-year increase in age. And then for women, it's 18% greater odds of 30-day readmission, and then so on down. And so if we have, like if we're transferred where we have an odds ratio that's less than 1 by 0.51, then that means that in this case, there's those that are transferred have 49% decrease in the odds of being readmitted at 30 days. And then for logistic regression, general linear models and generalized linear models, we need to look at how valid our results are. And so there's two statistics that we calculate, the C index and the calibration index. And so for our table here, it turns out the C index, or our model here of 30-day readmissions, is about 0.76. And so discrimination, when we calculate the C index, then if the value is 0.5, then we have no discrimination. In other words, it's just a coin flip whether between the two or more groups. If you get odds, or excuse me, a C index of 0.8, then we have what would consider really good discrimination. If it's like usually 0.6 something, then that's pretty mediocre, although I've seen studies where they think that 0.6 something is a really great discrimination index. And then the other statistic that we want to calculate is the calibration index. And so basically this is giving us an idea of where the predicted probabilities from our regression model are equal to the observed probabilities. And so the way that this is usually presented is a plot of observed probabilities with predicted probabilities. And obviously, if they're, if the prediction is perfect, then we're going to get a slope of 1 in our plot. And so here's an example of plotting the observed probabilities with the predicted probabilities. And so the dotted line there is the perfect calibration of 1. And so for the study here that's being represented, we have a slope of 0.97. So we have a pretty good indication there that our observed probabilities and predicted probabilities are really similar. Just to point out that the generalized model includes other analyses that we're not going to take time to go over, but we can do logistic regression with ordered outcomes like cancer stage, for example. We can do logistic regression with more than 2 outcomes where the outcome is nominal, that is, there's no particular order. And then Poisson regression is where our outcome is a count. And so, for example, if we want to look at, say, the number of ICU infections over a 3-month period, and in Poisson regression, if we exponentiate the coefficients, and we get what's called an incident rate ratio, and that would be analogous to the odds ratio in logistic regression. And then finally here, want to just talk about time to event models, which is another analysis that is very common in the research literature. And so we actually here have two outcomes. One is a dichotomous event, which could be death or could be recurrence. And then we have a time to that event. And we have to have a time from a point of origin to the terminal event. There's the concept of censoring is very important in time to event models, because some patients will drop out of the study or be lost to follow-up. So you don't really know whether they actually survived or not. But we can use their time up to the point of losing their information. And so those are called censored events. And then the survival function then is the probability that a patient survives from the time of origin to some point beyond a given time. The hazard rate is the probability that a patient dies at time t, conditional on having survived to that particular time. And then the hazard function and the survival function you can see are related. So if you know one, you can calculate the other. And then another concept that you will often see in time to event models is the median survival time, the time at which the survival rate is 50%. And then the other, or another important concept is the hazard rates over time, if they're proportional or non-proportional. And the easiest way to see this actually is looking at a plot of the survival functions. So in this case, the panel on the left, we would have proportional hazard. The lines, survival curves do not intersect. But on the right-hand panel, we would have non-proportional hazards in that the survival curves intersect. And I want to just spend a minute here on talking about multivariable survival models, the Cox proportional hazards regression. This is where then we can look at any number of coefficients or any number of independent variables that might influence survival. And we have the same kind of regression formula that we've seen in the other types of analyses. So I just want to give an example here where we looked at survival of PCI versus coronary bypass surgery and modeled this with Cox regression. And this has a twist to it that we need to consider when you have non-randomized groups. And so we use what's called inverse probability weighting, which is actually the inverse of a propensity score to equalize the two groups. And so the comparison here of PCI and CABG comes from two different databases. And so even though the statistical analysis is fairly straightforward by using the Cox model to look at variables that are related to the outcome, which in this case is all-cause mortality, then we first needed to somehow equalize the groups because obviously they're coming from different databases, different populations. And so this is the way that you do this with the use of inverse probability weighting. So you can see that in the unadjusted data, there's actually almost all of the clinical and demographic variables here are statistically different. Although because of the large number here, some of these differences are quite small. I would have sort of preferred to use standardized differences here rather than p-values. But once we apply the inverse probability weighting, then you can see that the differences become, or the p-value anyway, becomes quite a bit larger than the 0.001 for most of these. But that's when you have non-randomized groups, this is what you need to do in order to compare procedures or compare treatments. And so then our presentation here, a typical survival plot where usually you have an inset here where you get kind of like a close-up. And you can see that we have really non-proportional hazards here because at 30 days, the relative risk with CABG is higher than it is for PCI, 72% higher, in fact. But by the time we get out to 2 years, then the risk with CABG is almost or about 20% or so less than it is for PCI. So that's this is I think quite a good paper here illustrating both survival analysis or time to event analysis, and then how you compare non-randomized groups. Okay, so to finish up here, when you evaluate the statistical analyses of published research, so is there a primary outcome or are there also secondary outcomes? And then how are these handled from a statistical standpoint? Is there going to be adjustment for the alpha error rate, or do they not adjust for that? And then if we're doing modeling, as we looked at for logistic regression and survival analysis and general Lewin model, as well as how well does the model predict? And as I mentioned, then for non-randomized studies, you have to consider potential confounders, that is, variables that might affect the outcome or the whether it's the primary or secondary outcome that might affect the outcome as well as the treatments or therapies or whatever it is that you're comparing with your groups. So I'll end on that note there, and I'll have the slides again sent out, because I have a number of references here that relate to some of the concepts that we've talked about, primarily the use of or overuse of p-values, and then the one at the bottom there by Austin, as well as Yang and so on, look at using standardized differences in observational research. Let's see here. So let's see, I'm not sure we can communicate verbally here. Can you type your question in the I guess the Q&A or in the chat? Okay, let's see here. Yeah, I can't, let's see, I don't think there's any way that I can. Yeah, oh, here we go, okay. Um, so the comment is that it might be obvious, but making a type 1 error could be more dangerous than a type 2 error. Yes, that's true. A type 1 error is considered the error that you don't want to make. If you it's so if you have a say a outcome, or you have a treatment that's, say, has the possibility of more egregious side effects or like that, then you want to be really sure. So maybe you might want to, in that case, set your type 1 error at 0.01 rather than 0.05. And that is true that although I will have to say that it's really hard to change practice regardless of what your finding is, but the the type 1 error rate can change practice if it's set, or I would say, I'll say this: if the outcome is really important, then it might be better to set the type 1 error rate as smaller, and that's possible that it could change practice, whereas making a type 2 error isn't going to change anything. And you ever actually never know when you've made a type 2 error. So yeah. So anyway, I'll have the folks at Georgetown send these out if you would like to look at some of the slides or the references. So again, thank you for your time and attention, and then we'll meet again in the third Friday in March.